Welcome to today's paper reading. Today's paper is titled, GraphReader, Building Graph-Based Agent to Enhance Long Context Abilities of Large Language Models. This paper was published on the AR14 preprint by Shilong Li and colleagues from Alibaba Group. The authors introduce GraphReader, a graph-based agent system designed to enhance the long context abilities of large language models. The paper addresses the critical need for long context capabilities in large language models, LLMs, to handle complex tasks. Despite various optimization efforts, challenges remain in robustly processing long inputs. To tackle this, the authors introduce GraphReader, a novel graph-based agent system. This system structures long text into a graph and employs an agent to explore it autonomously. The agent analyzes questions step by step, devises a plan, and uses predefined functions to explore nodes and their neighbors. The exploration is course-defined, with the agent continuously optimizing its process. Experimental results show that GraphReader, with a 4K context window, significantly outperforms GPT-4-128K across various context lengths and demonstrates superior performance on challenging benchmarks. Large language models, LLMs, have significantly advanced in natural language understanding and generation. However, transformer-based LLMs face challenges in managing long context due to context window and memory constraints. Current techniques to address long context tasks in LLMs are categorized into model-level and agent-level approaches. Model-level methods involve fine-tuning with modified embeddings and transformer variants, while agent-level methods use retrieval-augmented LLMs. Despite these efforts, both approaches have limitations, such as high training costs and inability to capture multi-hop dependencies. To tackle these issues, the authors propose GraphReader, a novel graph-based agent that segments and compresses long text into a graph structure, enabling effective handling of long-range dependencies and multi-hop relationships. Figure 1 illustrates the performance of GraphReader on the LV-eval dataset across various context lengths. It shows that GraphReader consistently outperforms other open-source and closed-source models, maintaining a scalable performance even in very long contexts. In stark contrast, other models experience a marked decline in performance as the context length increases. In the realm of long-context large language models, LLMs, recent research has focused on positional interpolation, PI, to enhance long-context capabilities. However, these methods necessitate training on full-length texts, resulting in significant increases in data and training costs. To mitigate this, strategies like pose and skip-align have been explored, though they tend to overlook detailed information in long texts. Additionally, despite efforts to expand the context window, it remains constrained by a predefined fixed length. Transformer variants with modified attention mechanisms have been proposed to address these limitations, but they are prone to losing earlier information. Retrieval-augmented generation, RAG, leverages an extensive database of documents to aid in response generation. Research has investigated various levels of retrieval granularity, including tokens, entities, and chunks, as well as diverse retrieval methods such as BM25 and learning-based strategies. Despite its capabilities, RAG faces challenges in addressing complex questions due to difficulties in developing robust decision-making mechanisms. Recent work has increasingly leveraged LLMs as agents to tackle complex problems, utilizing their strong planning and reflection abilities. These abilities have been applied to complex tasks such as function call and KGQA. Agents are also capable of retrieving unstructured information, as seen in approaches like WebGPT, MEM-Walker, and ReadAgent. However, these approaches often struggle with multi-hop questions, and methods like KGP, which organizes documents into graphs, do not fully exploit the agent's capabilities for planning and reflection. The GraphReader approach is structured into three main phases: graph construction, graph exploration, and answer reasoning. In the graph construction phase, the document is split into manageable chunks, which are then summarized into atomic facts. Key elements are extracted from these facts to form nodes in the graph. During graph exploration, an agent is initialized with a rational plan to explore the graph. The agent explores atomic facts in chunks, updating a notebook with relevant information as it progresses. Finally, in the answer reasoning phase, all gathered information is compiled and analyzed using a chain-of-thought approach. The final answer is generated by the language model, considering all available information. Figure 2 provides a comprehensive overview of the GraphReader approach, detailing the three main phases: graph construction, graph exploration, and answer reasoning. In the graph construction phase, long texts are segmented into chunks, which are then summarized into atomic facts and key elements to form a graph structure. The graph exploration phase involves an agent autonomously navigating this graph, guided by a rational plan, to gather relevant information. Finally, in the answer reasoning phase, the collected information is analyzed using chain of thought to generate the final answer. In this study, the authors evaluated their approach on several long context QA benchmarks, including Hotpot QA, 2Wiki Multi-Hop QA, Musique, Narrative QA, and Hotpot Wiki QA Mixup. For evaluation, they used metrics such as F1 score, exact match, EM, and an optimized F1 asterisk score. They compared their method against baseline approaches including RAG with BM25 and ADA002, long context LLM with GPT-4-128K, and an agent-based method using read agent. The results indicate that their approach outperforms these baselines, especially in multi-hop long context tasks. Table 1 provides an overview of the benchmarks used in the evaluation of long context question answering methods. It includes statistics on the average and maximum number of tokens for each benchmark, as well as the total number of samples. The benchmarks are categorized into multi-hop QA, which includes Hotpot QA, 2Wiki Multi-Hop QA, Musique, and Hotpot Wiki QA Mixup, and single-hop QA, which includes Narrative QA. The token numbers are calculated using the GPT-4 tokenizer from TickToken, ensuring consistency and accuracy in the evaluation process. Table 2 presents the performance comparison of various baselines on datasets from Longbench. It highlights that BM25 and ADA002 methods show the poorest performance, while GPT-4-128K significantly outperforms RAG methods. Additionally, GraphReader demonstrates superior performance over read agent, indicating its effectiveness in long context tasks. Table 3 presents the performance percentages of various baselines on datasets from LVVal, highlighting the optimized F1 score denoted as F1 star. The table shows that GraphReader consistently outperforms other methods across different text lengths, demonstrating robustness with increasing context length. In contrast, the performance of GPT-4-128K full-text reading declines gradually as the input context length increases. This indicates that GraphReader remains effective in handling extremely long texts by leveraging graph exploration with limited context window LLMs. Table 4 presents the results of our ablation study, focusing on the impact of removing the rational plan and applying random node selection in graph exploration. The study reveals that the rational plan is crucial for guiding the agent in node selection and exploration, as its removal leads to a noticeable performance drop. Additionally, random node selection results in a significant decrease in performance, highlighting the necessity of systematic node selection based on reasoning. Overall, GraphReader consistently outperforms baseline methods across various text lengths, demonstrating its effectiveness in handling long texts. Figure 3 illustrates the performance of GraphReader across different initial node counts on the 2Wiki Multi-Hop QA and Narrative QA datasets. The results demonstrate the robustness of GraphReader to varying initial node numbers. Notably, the optimal performance is achieved with 5 initial nodes, which is set as the default. Beyond this number, performance declines, particularly in single-hop scenarios, likely due to increased noise from excessive initial nodes. Table 6 illustrates GraphReader's recall performance on Hotpot QA across different granularities. SF-wise granularity refers to the recall of supporting facts, while sample-wise evaluates the recall of entire samples. Despite the decline in recall as context length increases, GraphReader maintains around 60% recall at 256K context length, showcasing its scalability. Additionally, the recall in the final notebook is slightly higher than that of atomic facts, indicating the method's effectiveness in extracting more valid information from chunks during exploration. This paper introduces GraphReader, a graph-based agent designed to enhance the long context capabilities of large language models. GraphReader organizes long text into graph structures and employs an autonomous agent to explore the graph, successfully establishing long-range dependencies within a relatively small 4K context window. Experiments demonstrate that GraphReader outperforms GPT-4 with a 128K input length across various long context single-hop and multi-hop question-answering benchmarks. However, GraphReader is constructed using an off-the-shelf GPT-4 API, which may have potential restrictions due to its closed-source nature. Future work will involve collecting data, training models, and making them open source to contribute to the wider community. Additionally, the efficiency of the agent depends on its planning and reasoning capabilities, which will be explored in future research to improve the effectiveness of the method. Table 5 compares the token consumption per question between Read Agent and GraphReader on the Hotpot WikiQA Mixup 256K dataset. It shows that GraphReader uses only 1.08 times more tokens than Read Agent but achieves over twice the performance improvement. The average cost tokens for Read Agent are 48.7K, while for GraphReader, they are 52.8K. This demonstrates GraphReader's efficiency and superiority in handling long context question answering tasks. Figure 4 illustrates the effect of varying chunk size L on GraphReader's performance at the 256K length level of Hotpot WikiQA Mixup. The best performance is observed with a chunk size of L equals 2K. As the chunk size exceeds a certain threshold, performance deteriorates due to the model overlooking essential details. Conversely, smaller chunk sizes lead to semantic truncation, which hampers the model's ability to accurately extract atomic facts. Therefore, L equals 2K is selected as the default chunk size. Figure 5 illustrates the recall performance of supporting facts by various methods on the Hotpot WikiQA Mixup dataset. Notably, our model, GraphReader, consistently achieves higher recall rates compared to other baseline methods, irrespective of the input length. This demonstrates the effectiveness of our approach in accurately retrieving key information, which is crucial for tasks requiring precise knowledge recall. Thank you for watching.